Exercise 9 is the last exercise in this series on LDA. Here, we are going to explore the effect of shrinkage regularization on the accuracy, the performance of classification. And here we are going to use scikit-learn as you discovered in the previous exercise, so you don't have to worry about writing out the entire LDA on your own with, computing the covariance matrices and all that stuff. We're going to make it simple so we can focus on shrinkage regularization. You can implement shrinkage regularization directly in scikit-learn as an additional input parameter. And again, I'm not going to tell you exactly how to set that up, but I believe that you will be able to figure it out on your own. Okay, now the effect of regularization is something that I have discussed and also demonstrated in several previous chapters. As I note here, shrinkage will definitely reduce performance on the training data, kind of by definition. That's a little bit trivial. And the important question is whether the regularization improves the generalization, whether a model that is trained with shrinkage regularization can actually predict unseen data with more accuracy. Okay, and that's sometimes called a validation set. So the idea that you want to do here is to split the data into a test data set and a train data set. And the idea is that you fit the LDA to the training data, and then you evaluate its performance using the test data. Now, there's a few different ways you can do this. You can also split data into test and train using methods in scikit-learn. But in this particular case, I think it's just easier to do on your own. So I did it on my own. You can also, of course, use scikit-learn to solve this problem if you like. So what I did was randomly permute indices between 0 and 399. So basically one index for each of the data observations. And then I trained on the first 350 of these randomly permuted indices. And then I tested on the last 50 indices. Okay, now testing on 50 samples is not necessarily going to give us a really great estimate of the test performance. So therefore, I repeated this whole procedure, this test, train, split. I repeated that 50 times and then computed the average accuracy. Okay, and then that gives us a plot that looks like this. And let me see, I'll reduce the size a little bit. So here we are looking at the amount of shrinkage on the x-axis. You can see I do kind of extreme values. I go from 0 all the way up to 1, which is really extreme. But normally shrinkage would be much closer to 0. And then here is the prediction accuracy on the validation trials, or you can also call these the test trials. Okay, so it's pretty interesting to look at this. I'm going to interpret this. I'm going to have more to say about this function when I produce it in Python. So this code is not too difficult, but it is a little bit involved. You need a double for loop here. We have the first for loop that goes over the different shrinkage amounts. You can see I'm going from 1 to 0, 0 to 1 in 21 steps. And here I'm just initializing a vector to store all the accuracies. Okay, so here I set up the model exactly how we did it a few exercises ago. The only difference is here I'm specifying this optional input parameter for shrinkage equals s. Okay, and then here I have another for loop over 50 elements, and I'm using an underscore here because I don't actually need this looping index variable. I'm not going to do anything with this. I just want to run the same code 50 times. And what do we do in that code? So we randomly split the data. So I randomly permute numbers between 0 and 399. So this will just be, some completely random set of numbers between 0 and 399. And then what I do with that is I take the first 350 indices. Now this is not indices 0 to 349. This is the first 350 of these completely randomized indices. And I train on that. So these are the data observations. These are the labels. And that is to fit the model. And then I compute the accuracy, and the accuracy is actually predicted here. Okay, so I have LDA model. That's the model that we created. We fit it on the training data. And now what we are predicting is the test data. So here you see, instead of taking observations from the beginning to 349, I'm taking from indices 350 to the end. So these are the 50 test observations. And of course, we need the corresponding labels as well. So then we have these predictions. This is a Boolean of true and false. And then here I take the average, multiply by 100 to get percent, and append that onto the temp accuracy. So now this is creating a list of 50 test accuracy values for each iteration here. And the idea is that, all of this code is the same. The only thing that's different is which data observations are randomly selected to be in the training set and which are randomly selected to be in the test set. Okay, so then I take the accuracy at index I. This corresponds to the index for shrinkage regularization amount, and that's just the average of all of these accuracy scores. Okay, and then I make the plot. So it's a bit of code, but I hope you see that it's not so difficult. Okay, so this looks wild. This looks really, it doesn't look very smooth, but you can also see that the accuracy doesn't really change that much, right? I mean, this is 96.6%. So it's varying between, roughly around 96 and 97%. That is 1% variability. So this is really not something that you would spend a whole lot of energy interpreting. For example, we can change the y-axis limit. So I'll set the y-lim to be, let's go from 0.5 to 1. Remember that because this is two-class categorization, chance performance is 50%. So if you're doing more than 50%, then you're getting better than chance performance. Oops, this should actually be 100. So 50 to 100, like this. I'll run this again. So this shrinkage regularization, it looks like it was sort of bopping around chaotically, but this is really just due to just a tiny bit of noise fluctuations here. This is clearly no trends happening in here. And what do we make of this, considering that we get to such an extreme amount of shrinkage? Basically, what this tells us is that this problem is really easy to solve using a linear discriminant analysis. So this problem is sufficiently easy to solve that even though we're adding a lot of regularization, we're kind of decreasing the performance on the training set, but we're at a ceiling. So, it's so easy to solve this discrimination that there's really no point in regularizing at all. Nonetheless, this is industry standard code. When you run any other LDA analysis on more complex, more multidimensional data, the way that you use the code is exactly the way that you're using the code here in these exercises.